Hello, today I'm going to be talking about Kirchhoff's laws of circuits. And we know these laws conceptually already, but we're going to use them mathematically in order to figure out what's going on in a more complex circuit like this one. So Kirchhoff's laws are, there's two of them, and there's a voltage law, which is all about loops, and there is a current law, which is all about junctions. So we have a law about loops of current, so of circuits. So like this, that's a loop, that's a loop. This big one is another loop. We also have a rule about junctions, like this point and this point. So what Kirchhoff's law says for voltage is that the sum of all of the voltages around any single loop need to add up to 0. So if you start at a point, and we call that 0 voltage, and then you walk your way around a loop of a circuit, when you get back to that point, you have to be back down to 0 voltage again. And it doesn't matter where you start, it doesn't matter what loop you're on, it doesn't matter how many things are in the loop, that loop has to add up to 0 when you add up all the voltages around that loop. So there's the sum of the voltages around a loop has to equal 0, the loop law. The other law is the current law, or junction law, and we've seen this, but not in this formal mathematical sense. What the junction law says is that the sum of all the currents into a junction has to be equal to the sum of all the currents going out of that junction. So if we have a junction right here, and let's just say we have current going in, that means that the current coming out has to be equal. This is the same idea as conservation of charge, because current is just the number of charges going by per second. So if we can't create or destroy charge, that means that if we have 10,000 charges coming into this junction per second, we'd better have 10,000 charges per second leaving that junction. Now they split up, and how they split up depends on what's in that loop, but if you've got 10 going in, you'd better have 10 coming out. So we've gone over both of these conceptually before, but now we're going to use them mathematically in order to solve something that looks like this, which is a little more interesting, a little more difficult. The general rules for doing Kirchhoff's laws, when you've got a complex circuit like this, the first thing you want to do is define your currents. And we're going to define, for this one, two currents. We're going to say there's a current going around in this loop, and there's a current going around in this loop. Now you might say, well, what direction does it go? You make a guess. So you make your best guess based on what you see in that loop. And if you're wrong, it doesn't matter. The math will tell you if you're wrong. So the math will tell you if you just have it backwards. So make your best guess based on what you see going on in that loop. So here, for this loop, I've got a 12-volt battery pushing charge this way. I've got an 8-volt battery pushing charge back this way. So I might guess that the charge, since this is 12 volts and this is 8, that the charge goes this way around this loop. So I'm going to define the current around this left-hand loop as I1, so current number 1, and I'm just going to make a good guess that it goes this direction. With this second loop, I've got 8 trying to push it this way, 6 trying to push it back that way. All right, but I've also got 12 maybe adding. So here, you may not have your best guess. At this point, I'm just going to guess that the 8's going to overcome the 6. We'll see. I don't know what that 12 is going to do. So let's just make a good guess that current number 2 is going to go clockwise as well. So that's our first step for Kirchhoff's laws. Define your currents. And now what I recommend that you do is, for each resistor, draw the current and the direction of the current through that resistor. You don't have to do this, but it's going to help you. So if I1 is going this way around this loop, we've got I1 moving this way through the 10 ohm resistor. We've got I1 going this way through the 14. We've got I1 going down through the 6 ohm. I2, let's see. So I2 is going this way. So I2 is going downwards through that 2 ohm resistor, and I2 is going up through the 6 ohm resistor. Whew, okay, I think I got it all. And again, that step you don't have to do, but I find it very helpful. All right, so we've defined our currents. We figured out what the current is through every resistor. And now we're going to use the voltage loop law. The sum of all the voltages around any single loop has to add up to 0. So here I'm going to pick a starting point on a loop. So let's do the left-hand loop to start with. So this loop right here. And I'm going to pick a starting point. It doesn't matter what your starting point is. You can start anywhere in this loop. Personally, I like to start at the back end of a battery just because then I can always have the first thing in my equation be positive. And I like starting positive. So I'm going to start right here. The second thing is decide which way you're going around the loop. So we're going to walk our way around this circuit loop and add up all the voltages in that loop. So I'm going to start here, and I'm going to walk my way around the circuit going this way. And just like it doesn't matter where your starting point is, you can walk whichever way you want around the circuit. Your math will be the same as someone who does it the other way. So don't worry that there's a single right way. I just like to always start at the negative end of a battery and go positive for my first voltage. All right, so we know where we're starting, and we're going to walk clockwise around the left-hand loop. So for the left-hand loop, I'm going to add up all the voltages around that left-hand loop and set them equal to 0. Okay, so my first encounter with something is a battery, and I'm going in the same direction as the battery's trying to push charge. So what kind of voltage change do I have? Going from this end of the battery to this end of the battery, well, that's going with the direction that the battery is pushing charge. That's going in the direction of a positive voltage difference. So my first step is a plus 12 volts. So now I've gone from here, I've jumped up to here, and I'm 12 volts higher than where I started. Now I'm going to go across this resistor, and I have to figure out the voltage across that resistor. Well, we don't know what it is, but we do know that we can use Ohm's law. Ohm's law is still true for a resistor. So the voltage across that resistor is going to be the current through that resistor times the resistance. So the voltage across this 10 ohm resistor is going to be the current, which is I1, times the resistance, which is 10. All right, so the voltage is 10 times I1. 10 I1. But is it positive or negative? If you think about what's happening, voltage is a push, it's a pressure, and batteries provide that push or pressure to the circuit. What resistors do is use up that push or pressure. So if you go in the direction of the current, if you're walking around the circuit in the same direction as the current, then as you go across in a resistor, that voltage is going to go down. It's a voltage drop. So here, I'm going to say the voltage is dropping by an amount equal to I1 times 10 ohms. So that is the voltage drop across this resistor. Okay, so now I went from here to here, now I'm here, and I'm doing this left-hand loop, so I'm right here, and I'm going across a battery. But this time, I'm going across a battery kind of backwards. I'm going against what the battery wants to do. So in this case, instead of adding 8 volts, I'm dropping 8 volts because the battery's job is to provide an 8 volt difference going this way. So if we increase 8 volts going that way, I'm walking across the backwards way, I'm going to drop by 8 volts. So now I've gone here, I have to get my way across this resistor, and again, using Ohm's law, the resistance here is going to be voltage here is going to be the resistance times the current. I have 2 currents. and they're going in different directions. I need to take into account both of those currents because they add in that center branch of this circuit. That's the junction law. So in this resistor, I have both I1 going down and I2 going up. So that's how I'm using the junction law. The loop law, all right, so what's the voltage going from here across the 6 ohm? Well, with I1, I'm going with the current. So with the current means that it's a voltage drop. So I'm going to drop because of I1. And I'm going against the current for I2. So if I'm going against the current, that means it's a voltage increase, a voltage rise, plus 6I2. And these had better have different signs because the currents are going different ways. When you're walking in the same direction as the current, it's a drop. If you're walking in the opposite direction of the current, it's a rise. Okay, so now we're down to here. We got one more resistor. We're going with the current, which means it's a voltage drop, and it's going to be, I ran out of room, 14 times I1. Now I'm back to my starting point, which means that I have to set all of those, I add them all up, set them equal to 0. So that's the equation for the left-hand loop, for this loop right here. Looks kind of messy. Let's simplify it. I've got straight up numbers, I've got I1s, and I have a single I2. So let's simplify that down. A plus 12 and a minus 8 gives me a plus 4. Okay, I1, minus 10 I1, minus 6 I1, minus 14 I1. That should be a minus 24 I1. How many I2s do I have? A plus 6 I2. Okay, so let's just double check. Do I have that right? Oops, I did something wrong. Oh, 16 plus 14. Good thing I checked my notes, huh? Hopefully you caught that. I've got 10 plus 6 is 16 and 14 is 30. All right, good. So I have an equation for I1 and I2. Now a single equation isn't going to do me any good because if I have two unknowns, I need two equations in order to solve for those unknowns. So let's find another loop and get a second equation. All right, so we did the left-hand loop. Let's try the right-hand loop. Right-hand loop. We're going to do the same thing. We're going to add up all the voltages around that loop, walk around that loop, set them all equal to 0. Okay, and again, where do you want to start? Which way do you want to go? Doesn't matter. So long as you're just consistent as you walk around, it'll be good. I like starting at the negative end of a battery just because then I start with something positive. So I'm going to start here, and I'm going to go counterclockwise around this loop. All right, so going from here to the top of that battery, I'm going with the battery, so it's an increase in voltage, plus 6 volts. Now I'm going from here to here across this resistor, but I'm going against the current. Against the current means it's a voltage increase, and the voltage itself is going to be I times R, which is 2 times I2. So I'm here, now I'm going down. I'm going across this battery, but again, I'm going against it. So I'm dropping 8 volts when I go from here to here. Then I have this resistor, and again, I've got two currents going through that. One's going down, one's going up. I got to take into account both of them. Now this time I'm walking down, so I'm with I1, which means it's a voltage drop, minus 6 I1, and I'm going against I2, so that produces a voltage increase, and now I'm here, gets me back to start, set it equal to 0. So there's my second loop, and again, let's simplify it so I have the same format. Number, I1, I2. 6 minus 8, negative. Oh well, I tried. I1s, how many I1s do I have? A negative 6 I1, and a plus 2 and a plus 6 I2 gives me a plus 8 I2 equals 0. Okay, does that match what I had before? Minus 2, minus 6, plus 8. Got it. At this point, I could use these two equations to solve for I1 and I2. Two unknowns, two equations. However, to make my life a little bit easier, I'm going to find a third equation because that could mean things are a little bit easier. And you might say, well, where is the other loop? How are you going to get another loop out of this? So we had a left-hand loop, which was this one, and we have a right-hand loop, which is this one. There's a third loop. Can you figure it out? See if you can think about what's that third loop. And it may not look like a loop, but there is another path you can take around this circuit. And that's going around the outside. So we have the outer loop that we can also do the voltage law on. Okay, so where should I start in this one? Well, let's just start there. I already have two starting points, they both work. And again, it doesn't matter where you start, and it doesn't matter what direction you go, you will get the same equation. If you do clockwise and your lab partner does counterclockwise, you'll just have all the signs reversed. Where you have a plus, they'll have a minus. Where you have a minus, they'll have a plus. So don't worry about direction you choose or starting point. I'm going to start right here and walk my way clockwise around this outer loop. All right, so from here to here, we're jumping up plus 12 volts. And then we're going across this resistor. So it's with the current, so it's a voltage drop, and the voltage is 10 times I1. That brings us here. Now we're going across this 2 ohm resistor. We're going with the current, so it's a drop. The voltage is 2 times I2. That gets us to this point. Here we have a battery, but we're going against what the battery's trying to do. So that's a drop, minus 6 volts. Brings us over to this resistor with the current, voltage drop, and the voltage is 14 times I1. Back to start. Add them all up, set them equal to 0. Simplify this one. We've got a 12 and a minus 6, giving me a plus 6. I1, I have a negative 10 and a negative 14. So minus 24 I1, I2, I've got a minus 2 I2. Okay, so here is my third equation. Plus 6 minus 24 I1 minus 2 I2 equals 0. What do I do with this? And at this point, we've solved the physics. Now it's solving the math to find our answers. If you have a preferred way to solve simultaneous equations, go ahead and use it. If you want to solve one of these for I1 equals and then substitute it into another equation, that works. If you want to do this as a matrix, that works. I'm going to show you a different way to do it that's often very handy when we have something like this, and kind of with these nice numbers. I'll call them nice numbers. Let's look at these three equations. All right, so I'm going to rewrite them all together to kind of look at them all in one area. So the left-hand loop, I've got that one up here, and then I'm going to rewrite the right-hand loop and the outer loop above them. So minus 2 minus 6I1 plus 8I2 equals 0, and then plus 6 minus 24I1 minus 2I2 equals 0. Okay, so I have 3 equations and 2 unknowns, so I have more information than I need, but that can be very helpful because sometimes the numbers are not very pretty, and if the numbers aren't very pretty, you might want to make your life a little easier with solving the simultaneous equations. I do try to make the numbers roughly reasonable, so these are all, everything's even, for instance, and they're all in the same range, between 2 and 14. I won't give you something where I have 2 ohms and then another resistor might be 300 ohms. I'm going to try to keep things a little more simple than that. All right, so we have 3 equations and 2 unknowns. And again, if you have a different way to solve it, go right ahead. This is just one way that's kind of interesting and fun, given this kind of a setup. Let's do a different color. Okay, I'm going to call this equation A, and equation B, and equation C. I want to do something to come up with an equation that gets rid of one of my two unknowns. Maybe it gets rid of I1, maybe it gets rid of I2. So I can look and say, are there any convenient multipliers or numbers that match up really well? There's no identical numbers here, but you might say, well, 6 goes into 35 times. 6 goes into 24 4 times. 2 times 4 is 8. 2 times 3 is 6. You can look for these kind of matching numbers so that you can come up with different ways to add or subtract the equations to get rid of one of your unknowns. Let me show you what I mean. Let's start with, which one did I choose? 4b minus c. Why did I choose that? So if I were to take equation b, multiply by 4, and subtract equation c, what would I end up with? Okay, 4b and minus c. Oh, I have these in a different order. Let's try putting them in the same order that my notes are in. 4, I'm guessing 4, yeah. So, 6 times 4, what do I have? 4 of this one, so 4b minus the 6 and 24, minus a. There we go, that matches my notes. I'm going to rewrite the two equations as 4b and as a. 4 times b. Okay, 4 times minus 2, minus 8. 4 times negative 6, minus 24. 4 times 8, plus 32. And 4 times 0, still 0. And minus a. So what's minus a? Well, I had a plus 6, that becomes a minus 6. A minus 24i1 becomes a plus 24i1. Minus 2i2 becomes a plus 2i2. And negative 0 is still 0. And now I'm going to add these two together. So I'm just going to line up, literally line up each of these columns and see what they add up to. Minus 8 and minus 6 is negative 14. Here's where the nice trick happens. Negative 24i1, positive 24i1. I1 is out of the equation now. Plus 32i2 plus 2 gives me plus 34i2. 0 plus 0 is 0. Now I have an equation without I1 in it. I can solve this for the current in the second loop. And so bring this over to the other side, divide 14 by 34, and you will get, what do you get? 0.412. 0.412 amps. Okay, so we have a number for current number 2, the current in this loop. How can we get the current in number 1? Well, I have 3 different equations here, and they should all get me the same thing, because current number 1 doesn't change just because I went around a different loop. So if I plug I2 into all 3 of these equations, they'd better all get me the same thing. And now this is where I'd recommend you hit pause and do this. Plug in I2 for all of these and solve for I1. When I did it, equation A, I got I1 equals 0.216 amps. With equation B, I1 equals 0.216 amps. And equation C, I1 equals 0.216 amps. So I'm pretty confident that I1 is 0.216 amps. All right, now both of these numbers ended up positive, which means that we got both of these directions correct. We guessed this direction correctly, and we guessed this direction correctly. If one of these had come out negative, it would have told us that, oops, we guessed wrong, it's actually the other way around. So positive values tell you you've guessed the direction right. A negative value for the I's, the currents, just means you guessed the direction, it's actually the other way. And one of the other nice things is that you can check your answers one more time, because now we have an equation for a value for I1 and I2. So you can go back in, plug this value in for I1, plug this value in for I2, and add them all up, should be 0. You have 3 different checks. So here's one of the ways to check your answer makes sense, because all 3 equations should have given us the same answer for I1. All 3 equations should give us 0 when we add them all up, now that we know I1 and I2. So that's one way to do it. Now, if you go back to this step, where I decided for B minus A, you might have seen another multiplier, I guess I'd call it. You might have said, well, why didn't you do like 6 times 5 and that would give you 30? That would work. It will give you exactly the same numbers. So it doesn't matter how you solve these equations, how you put them together, or how you solve the simultaneous equations, you will get the same answer. A couple of the ones that I saw would work. Let's see. I saw that A minus 5, oops, A, not A. I got the wrong versions here. The 4. So C minus 5B. Let's see. So if C minus 5B, well, 6 times 5 is 30. That would get rid of I1. Another one is C plus 3A. What would that give us? C plus 3A. 3 times 2 would get me 6. That would get rid of the I2. So those are just 2 more examples of how you could combine the equations and still come out with I1 and I2. If you're feeling like it, give it a try. Rewrite the equations, C minus 5B, add up all the columns. You should be able to solve for one of the currents. Try another one, C plus 3A. Or try making up one of your own, because you can have, there's tons of different variables here. You've got lots of choices. You could have multiply this equation by 4 and then add it to this one. That would get you rid of I2. The only thing to be careful of is you don't want to get rid of the numbers, the pure numbers, because then you're left with an equation of I1 and I2. It doesn't help you at all. We need to get rid of either I1 or I2 so that we're left with a pure number and one of the variables, so that we can end up figuring out what the number is. So that's the idea behind Kirchhoff's laws. The voltage law is how we get our equations, and then the junction law, the current law, is just this idea that in this branch right here, we have current going from I1 going down, and we have current I2 going up. And so that's the basics of Kirchhoff's laws. And one of the interesting things about this, in terms of practice, is that you can make up whatever circuit you want and see if it's going to make sense. You can try the math, and if you get the same answer every time, you probably did it right. And then you can go back again and check. Once you have your I1 and I2, dump them back in here. And again, you have a check that does your answer make sense mathematically? Is everything adding up to the right thing? So that's a good way to do some practice with these. You probably can see that it's nice to keep like everything even, or do like factors of 5, so make this a 5 volt, a 10 volt, a 15 volt, and then have everything be factors of 5. Those are just some ideas to make your life a little bit easier. I like keeping it in terms of the evens most of the time. But even with all of these numbers being even numbers up here, you see that our answer was not a nice number. The last thing I want to show you is just what a good answer would look like. So my questions are really, what is the current in every branch of this circuit? And one of the ways to answer would be I1 is I can round at this point, 0.22 amps, and the direction is clockwise. So that would be one way to show it. Round that off to 0.41 amps, and the direction, we had it right, was clockwise again. So that would be one way to show the answer, because you've defined I1 and I2 in your picture, and then you've given me what I1 and I2 are. I know everything about this circuit, or I can figure it out. So this is a good way to give your answer. Give me what the current is, what the value is, and the direction. Okay, so that's Kirchhoff's laws. I hope this was useful. Good job.